From Statistics to Systems, Integrating Probabilistic and Deterministic Modeling in Medical Research, number 1400, October 22, 2025. Gerald C. EclaireMD Foundation. Category, Methodology. Mission Statement. I write these medical papers not for fame or recognition, since I have already lived a long and successful life, though not always a healthy one. My purpose now is to share what I have learned about health, disease, and medicine, so that others can better understand their own conditions, prevent illness, and live longer, healthier lives. Preface. Throughout my 16 years of medical research, I have relied primarily on system-based and deterministic frameworks to study chronic diseases, cardiovascular disease, CVD, chronic kidney disease, CKD, dementia, cancer, stroke recovery, the aging process, and longevity. My GH method, which includes 3 analytical domains, time, frequency, and space, together with the energy model of Viscoplastic Medicine Theory, VMT, and the geometry model of Topological Data Analysis, TDA, has helped me describe the human body and its health conditions as a dynamic, nonlinear, and energy-driven system, rather than a collection of isolated biomarkers, as viewed in traditional clinical medicine. In October 2025, I completed another small step in my methodological exploration, a stochastic modeling study based on probability analysis of my post-stroke memory recovery over 17 weeks. This research reminded me that randomness and uncertainty also play some kind of important roles in biological systems. While my deterministic models have the advantage of explaining causal mechanisms, particularly in personalized medicine, using my own dataset of more than 4 million records, stochastic modeling helps illustrate how order gradually emerges from randomness, chaos, toward healing, stability, especially when applied to large populations. However, this kind of insight can also be explored through deterministic research models, such as VMT and TDA. Those extreme cases, often categorized by statisticians as outliers, are in fact critical to patients' lives, since many involve mortality-related diseases. In this particular article, my only probability-based research paper thus far, I share what I learned from combining these different perspectives, and how this experience expanded my understanding of medical research methodology, even though it did not alter my fundamental preference for deterministic approaches. Deterministic and stochastic thinking. In most of my research, deterministic modeling has been my focused foundational tool. The VMT model treats each health variable as a stress-strain system, governed by energy balance and irreversible dynamics. When I apply these equations to weight, glucose, blood pressure, or stroke recovery, I can visualize how biological processes behave under internal and external stress. Deterministic modeling gives me causality, it tells me why something happens. Stochastic modeling, on the other hand, deals with probability of uncertainty. It recognizes that biological systems contain inherent randomness, due to countless interacting variables. Instead of fixed outcomes, we see distributions of possibilities. This approach is powerful when quantifying uncertainty, estimating risk, or describing large populations. The problem in modern medicine is that we often stop there. We use statistics to describe variation but rarely to uncover mechanism. I believe this imbalance has slowed medical advancement compared with other branches of science, such as physics or space engineering, where deterministic laws come first and probability serves only to refine them. My application of stochastic modeling. In my recent stochastic study, I analyzed 17 weeks of memory test data, collected after my recent hemorrhagic stroke on June 21, 2025. Each week included 7 sets of daily trials, and each set contained 20 test items, allowing me to treat the data as a series of binomial events. Binomial events refer to outcomes that can fall into only 2 categories, for example, success or failure, yes or no, or correct versus incorrect. In recalling memory test items, using Bayesian updating, I calculated how my recovery probability evolved week by week. In the early weeks, my results fluctuated widely. By week 9, the curve approached near certainty, indicating that my memory recovery had reached a stable plateau. As data accumulated, my posterior confidence increased, reflecting a gradual stabilization process similar to neuroplasticity. In Bayesian statistics, posterior confidence represents my updated level of certainty about a probability after incorporating new evidence or data. As I continued collecting more information over the 17 weeks, my uncertainty steadily decreased, and my posterior confidence in the recovery trend became stronger and more reliable. I then used logistic regression to link my memory recovery probability with behavioral factors, such as walking steps, sleep hours, heart rate, systolic blood pressure, and pulse pressure. Walking activity emerged as the strongest contributor, confirming the key role of moderate physical movement in memory rehabilitation. This stochastic framework allowed me to measure uncertainty and observe how confidence developed over time. It complemented, rather than replaced, my deterministic VMT analysis, my earlier viscoplastic energy model, had already demonstrated how behavioral stressors translated into recovery strain, while the stochastic model added a new dimension, quantifying the confidence and stability that I had previously inferred through deterministic methods such as VMT and TDA. Why deterministic foundations matter. Despite the usefulness of stochastic tools, I remain convinced that deterministic reasoning must form the core of medical science. Biology operates under physical and chemical laws, energy conservation, thermodynamic irreversibility, and material deformation. All govern how cells, tissues, and organs behave. These principles give structure and predictability to life processes. Statistics alone can describe what happens, but it cannot reveal why. Randomized trials and regression analyses are valuable for population inference, yet they often hide individual mechanisms behind averages. The sickest or most unique patients, the outliers, are precisely those whose data can reveal the system's real dynamics. Deterministic modeling treats these outliers not as noise, but as signals that define the boundaries of biological behavior. In my own case, the VMT energy model explains the mechanism of recovery. Stress inputs such as walking and sleep provide healing energy that is gradually absorbed by the brain's viscoelastic, or viscoplastic material system. The stochastic model then quantifies how consistent and confident that healing becomes over time, building a hybrid framework. Through this experience, I have come to see stochastic and deterministic modeling as complementary rather than opposing tools. Deterministic models describe the skeleton of the system, the mathematical and physical rules that define its fundamental behavior. Stochastic models add part of the muscle and skin, the variability and uncertainty that make the system alive. When combined with topological geometry, they form a complete picture. Physics provides causality, VMT. Mathematics provides structure, TDA. Probability provides confidence, stochastic modeling. This integrated approach moves medicine closer to predictive control engineering, where we not only observe disease but also simulate and anticipate it. By merging these models, I can capture both the order and the randomness inherent in biological recovery, a reflection on the culture of current medical research. During my past 16 years of medical research, I have noticed that the culture of medical science often prioritizes statistics as the ultimate proof of validity. While statistical methods are essential, they are not sufficient for understanding complex biomedical systems. In engineering, physics, and chemistry, deterministic equations come first. Experiments and statistics only verify those theoretical equations. Medicine must follow the same path if it hopes to achieve the same level of predictive precision. However, in the current curriculum of most medical training institutions, mathematics and physics are not required courses for medical students. I believe that the future of biomedical science lies in uniting these two languages, deterministic causality and stochastic uncertainty. Each patient is a system of equations with built-in randomness. Each dataset contains not only statistical patterns, but also mathematical principles and physical laws. The task of modern medicine is to discover both, not just one. A common mechanism across VMT, TDA, and stochastic models, the strain change rate of time, d epsilon dt. Through my cross-model observations, I discovered that the strain change rate over time, d epsilon dt, serves as the common core mechanism linking viscoplastic energy reduction, geometric shape contraction, and the probabilistic transition from chaos to stability. This conclusion emerged after writing more than 700 medical research papers, applying the principles of viscoplasticity. In my VMT energy model, a slower strain rate means lower internal energy dissipation, indicating recovery and system stabilization. In my TDA geometric analysis, this same slowing corresponds to the shrinking and smoothing of topological shapes, reflecting improved order within the system. In the stochastic framework, decreasing strain fluctuations narrow the probability distribution and raise posterior confidence, showing randomness evolving into stability. Across all three approaches, reduced strain change rate represents the universal sign of healing. Less internal friction, greater coherence, and higher certainty. It unifies the physical, geometric, and probabilistic perspectives into one consistent interpretation of biological recovery. I believe that my 42 years of interdisciplinary study in mathematics, physics, engineering, business administration, marketing, economics, and medicine have helped me recognize this core common denominator or shared mechanism. By understanding how systems behave through energy, geometry, probability, time, space, frequency, and biomedical phenomena, I could see how the same principle of strain change rate connects viscoplastic energy reduction, geometric contraction, and probabilistic stabilization across multiple mortality, diseases and overall health issues. I do not consider this insight unique, but rather a natural result of applying fundamental scientific reasoning to medicine. During my past 16 years of medical research, others with similar interdisciplinary training could likely reach the same conclusion. once they view biological and biomedical processes as dynamic systems, governed by universal physical laws supported by a strong mathematical foundation. Conclusion: my stochastic modeling study of post-stroke memory recovery taught me that the healing process can be understood through both deterministic and probabilistic laws. However, the probability-based approach reveals only part of the picture. The deterministic approach can uncover deeper and more comprehensive insights that statistical methods alone are unable to achieve. The deterministic side governs the physics of recovery. The stochastic side describes the variability of human experience. When these frameworks are integrated, they create a more complete and realistic view of life itself. Medicine should not remain merely a statistical science. It must evolve into a dynamic systems discipline, founded on a holistic systems perspective, one that simultaneously measures energy flow, maps topology, and quantifies uncertainty. This integrated approach will enable future physicians and researchers to move beyond symptom description and medication prescriptions, advancing instead toward precise prediction, effective prevention, and truly personalized control of each patient's health. Disclaimer: this content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.